Let's take a look at a couple of the practice problems from your textbook. So the first one is, and I think this is page 569, it's chapter 12, so end of chapter problems, chapter 12. So if we look here, number 31, we're given some data. So again, let's see, we're going to go to the TwoStats app and so put in my data. And we're going to ignore the plus or minus one. We're just going to put in the raw data. So 120, 300. Whoops. Let's try that again. 100. Okay, so there's my data. And let me go back to my symbolic view and make sure, again, I'm checking for zero order with S1, and I'm checking for first order with S2, and I'm checking for second order with S3. I'm going to hit the plot key to make it use the data. And then again, just so that I can see what it looks like. Here's our check there. Now I'm going to go back to my number view and stats. And in looking at my R squared, I see that S2, so it is first order. So the question, first it says determine the rate law. So the first order rate law, and our reactant here is hydrogen peroxide. So our basic rate law, oh, I thought I had it chosen, is going to be, make sure my pen is working here. So it's going to be rate equals K H2O2. So if they just ask for what is the rate law, it's that standard form that we've been using. And then it says the integrated rate law. So since it's first order, my integrated rate law is going to be the natural log H2O2 is minus KT plus the natural log of the initial H2O2. And it says the value of the rate constant. So I'm going to go back to my symbolic view and down to that plot. And I'm getting that my rate constant is 8.3498 times 10 to the negative fourth. And the units on that, since it's first order, and my time was in seconds, so it would be seconds to the minus 1, 1 over seconds. And then the next thing, it says calculate the concentration at 4,000 seconds after the start of the reaction. So now I'm just going to plug in my numbers. So the natural log of the H2O2, that's what I'm trying to find. So minus 8.3498 times 10 to the minus 4. And then my time, and we're going to expand this out a little bit. Oops, I didn't mean to do that. Give us a little more room. So there's that times 4,000, and then plus the natural log. And I go to my data, and at time 0, it is, my concentration is 1. So we get that, I'll plug that in, negative 8 4 times 4,000 plus, let's here, let me move this over a little bit. So you can see the calculator. And of course, now I'm typing into my function thing. I don't want to do that. So we're going to say okay. And we're going to go back to the function. And now we're going to plug it in. So negative 8.3498 EE negative 4 times 4,000 plus the natural log of 1. Hit enter, and I get that the natural log of H2O2 is going to equal negative 3.34. And then, so I'm going to do the inverse log. So H2O2 is going to be E to the negative 3.34, which is equal to, so I'm going to do shift natural log to get that key there. And then we're going to plug in that and say enter. And so I'm getting 0.0354 would be the molarity at 4,000 seconds. Okay, so now let's take a look at number 32. So here it says, it gives us a reaction, and at a particular temperature, it gives me my, so this value here, that's my A naught, and it says a plot of natural log of A versus time. So remember I said that was one of the ways they can give you what order it is to tell you which graph works. So that it means it's first order. And it says with a slope value of, so the positive value of that slope is going to give me my K. So it says determine the rate law, the integrated rate law, and the value of the rate constant. So rate law, we have rate equals K times A. Integrated rate law, natural log of A minus KT plus natural log of A naught. And our rate constant is the positive value of our slope, so 0.0297, and that's minutes to the minus 1. And then that's part, that was A. B says calculate the half-life. Well, our equation, and this is on your formula sheet, for first order, the equation for half-life is 0.693 over K. So 0.693 divided by 0.0297 gives me a half-life. And again, the K is in per minutes. So that means my half-life value will be in minutes. 0.693 divided by 0.0297. So I'm getting 23.3, and that's in minutes. And then C, it says how much time is required for the concentration to decrease to. So that's giving me the A value, and it's wanting the time. So we have the natural log. I'm probably going to have to make this screen bigger. Let's run that out a little bit. The natural log of 0.0025 is equal to negative 0.0297, solving for time, plus the natural log, and it told us that that initial value was 0.02. Okay, so now the natural log 0.0025. So I'm getting a minus 5.99 is equal to negative 0.0297 times t plus, and then natural log of 0.02 is a negative 3.912. All right, so negative 5.99. Then we're going to go plus 3.912. And so I get negative 2.078, and that's equal to minus 0.0297 times t, which will give me a time of, let's see, I'm going to divide that by negative 0.0297. So I'm getting a time of about, we'll just round it and say about 70 minutes. All right, so that's part C. Okay, problem 33. So for here, we're going to go back into our two variable statistics. Let me get the screen back visible. All right, so so 0, enter, 1200, 3000, and then let's delete, oops. Deleting out this extra data there from the other problem. Okay, and so 0.5, 0.444, 0.381, 0.34, 0.25, 0.174. And so again, we're going to go back, make sure I didn't mess anything up with my symbolic. Okay, that all looks good. So now I go to my plot. Okay, then back to number view, stats. So it's looking like this one is second order because S3 is my best fit. So it says determine the rate law. So my rate law, rate equals, and it's K, and then NO2 was the reactant, and it's second order. And the integrated rate law then is going to be 1 over NO2 is equal to KT plus 1 over NO2 naught. And then my K value, I'll go back to my symbolic view and down to the second order plot. And that is showing me that the slope is 2.098 times 10 to the minus 4. And then because it is second order, I'm going to have molarity to the minus 1 and seconds to the minus 1 as my unit for my K. And then it wants the NO2 at the given time there. So 1 over NO2 is going to equal 2.098 times 10 to the minus 4 times, let's make a little more room here, whoops. All right, times 2.7000 seconds plus 1 over, and then looking at the data at time 0, it's 0.5 concentration. Okay, so we get 2.098 10 to the negative 4th times 27,000 seconds plus 1 divided by 0.5. And, oh, I did it again. I keep forgetting. Let's go back to my function view. Now let's try that again. Okay, so I'm getting that 1 over the NO2 is equal to 7.66, which means that the NO2 is equal to 1 divided by that number, which is 0.1305. All right, and our last practice problem here from the book says here, number 34, a certain reaction has the following general form. So it's given us our A naught. Here again, a plot of 1 over A versus time. That means it is second order. And then it gives us the slope, which is, that right there then, that's our K value. So it says determine the rate law. So we have again, so A, part A is rate equals K. A is our reactant squared. The integrated rate law, 1 over A is KT plus 1 over A naught. And my K value is 3.60 times 10 to the minus 2, and it's second order, so that's m to the minus 1, and it is, I guess it's per second, so seconds to the minus 1. So B says, wants the half-life. Okay, so now you could go back and look at the formula. But the key thing here to remember is that at the half-life, so at T1 half, my A is equal to 1/2 of my A naught. And it doesn't tell us to start anywhere but from my A naught. All right, so I'm going to say that my A then is going to be 1/2 of the 2.80 times 10 to the minus 3. Okay, so that's going to be 0.5 times 2.8, 10 to the negative 3. So I'm getting 0.0014. And then I'm just going to plug that into the equation. So 1 over 0.0014 is equal to my K was 3.6 times 10 minus 2. I'm solving for, and I can go ahead and say this is T1 half, and then plus 1 over 0.0028. Right, 1 divided by 0.0014. Oh. So I'm getting, come up a little bit, 714.3 is equal to, let's just get that out scientific notation, 0.036 times T 1/2 plus, and then 1 divided by 0.0028. So 357.14, then 714.3 minus that equals 357.16, 0.036 times T 1/2. So my half-life is going to be that divided by 0.036. So I'm getting a half-life of 9,921 seconds. Okay. All right, and then now let's put a little bit of room in here. So insert space, right? So I can finish the problem here. Okay, so part C on this, and going back up, says how much time is required for the concentration to decrease to 7 times 10 to the minus 4. So I'm going to have 1 over 7 times 10 to the minus 4 is 3.6 times 10 to the minus 2 times the time, and then plus 1 over 0.0028. And so simplifying that, you get 1 divided by 7, 4. So I get 1428.6, and that's 0.036 times time. Plus, and then that's still going to be 357.14. And that minus 357.14, giving 1071.4. And then my time is that divided by 0.036. So I get a time of 29,762 seconds if I round it to the ones place.